everyone, in this video I'm going to go through 3 different examples of simultaneous move games. In a previous video that I will link to in the description below and above, I explained solving for Nash equilibrium, identifying dominant strategies and dominant strategy equilibrium, and also how to understand the setup of simultaneous move games. So please go there first if you need to know more about these concepts. This video is intended as a practice video and might be too quick or not explanatory enough if you're completely new to simultaneous move games. Alright, let's start with this one. We have 2 players, Don and Mike, and each player can either go up or down. Don is in the position of player 1, which is to the left of the grid, and Mike is in the position of player 2, which is above the grid. So in the cells, the first number corresponds to Don's payoff, and the second number corresponds to Mike's payoff. The first thing I'm going to do is find our best responses for each player. I can start with Don's best responses first to each of Mike's possible actions. If Mike goes up, we're on this column here. Don could go up and get 10 or down and get 0. The best response here is for Don to go up because 10 is greater than 0 and Don wants the highest payoff possible. I'm going to underline under 10 in order to indicate this. If Mike goes down, we're now on this column here. If Don goes up, he gets 7, and if down, he gets 15. Again, since 15 is greater than 7, Don's best response is to go down. Note that Don does not have a dominant strategy since his best responses change with what Mike does, and so there's not one action that he should take regardless of whether Mike goes up or down. Okay, now we've gone through Don's best responses, we can switch and consider Mike's. If Don goes up, we're on this row. Remember that Mike's payoff is the second number listed. So if Mike goes up, he gets 5. If down, he gets 8. 8 is bigger than 5, so the best response here to Don going up is for Mike to go down. What happens if Don goes down? Well, we're on this row here. Mike could go up and get 6 or down and get 7. 7 is larger than 6, so Mike's best response is to go down. We can note here that Mike, in contrast to Don, has a dominant strategy because whether or not Don goes up or down, Mike's best response is to go down. So down is a dominant strategy for Mike. Great, so we can see here we have one Nash equilibrium with this game, and it's down, down. And I can tell that because Nash equilibrium are intersections of best responses. At down, down, we have 2 underlines in our cells. That is to say, if both players play down, they would be playing best responses to one another, and no one would have an incentive to deviate given what the other person is doing. Okay, that's it for this game. Let's go to the next one. We have Janice and Fatima, who can each go to the left or to the right. The first number of the payoff belongs to Janice, and the second to Fatima. Let's start by finding Janice's best responses to each of Fatima's possible moves. Okay, if Fatima goes left, we're on this column here. If Janice goes left, she would get 100. If right, she would get 0. Again, as before, since 100 is greater than 0, Janice's best response to Fatima going left is to go left. If Fatima goes right, then Janice could go left, in which case she would get 0. Or if Janice went right, she would get 50. So the best response is to go right here because 50 is greater than 0. Okay, let's switch it around and think about Fatima's best responses to Janice's possible actions. Well, if Janice goes left, we're on this row here. Fatima could go left and get 100 or right and get 0. And so left is our best response. If Janice goes right, we're on this row here. Fatima could go left and get 0 or right and get 50. So right is a best response. Great. So actually, when we think about our Nash equilibrium, there are 2 Nash equilibria here, which are left, left and right, right. This is an example of a coordination game, which is characterized as there being no dominant strategy for either player, which means that for both of our players, their best response changes depending on what the other player has to do. So these guys need to coordinate their responses with one another. The two Nash equilibria here correspond to the two outcomes where our players coordinate together. A model like this can be used to describe situations where what matters is coordination. For instance, if we're deciding what side of the road to use or what a particular symbol means, in these interactions, what matters is that each of the players in the game coordinate together, driving on the same side of the road or taking a symbol to mean a particular but the same thing. Here I've created the game so that both individuals would prefer the outcome to be left-left. This shows that while right-right is a Nash equilibrium, it's not the best place to be, and it's not Pareto optimal. If we were at right-right, both of our players could do better if they coordinated together and went to the outcome left-left. So Nash equilibrium does not mean that it's the best place or optimal. It's just a stable place where every player is playing a best response to one another, and no one would benefit from changing their action given what the other players are doing. All right, let's go to the last one. This is a really interesting and probably my favorite type of game. In the example that I have set up here, we have two companies that are in the market for some good. They can either cooperate together and both collude and set their prices high, in which case they would share the market and both get $20. The bottom left outcome is where Company A prices low and Company B prices high. In this case, Company A is going to steal all of the market and get $40, and Company B gets $0. Likewise, if Company B prices low and Company A prices high, we get to the top right outcome. Company B in this case is going to steal all of the market and get $40, and Company A gets nothing. If they both price low, they share the market but get a lower profit than they would have if they shared the market and both priced high. As before, we can solve for the Nash equilibrium by finding the best responses. Let's start with Company A. Okay, well, if Company B prices high, we're on this column here. Company A could collude with Company B at this point and get $20 and share the market. But if they price low, they're going to take the whole market and get $40. So the best response for Company A is to price low if Company B prices high. If Company B prices low, we're on this column here. Company A could price high, in which case they would get $0, or price low, in which case they would get $10. So the best response here is again to price low because 10 is bigger than 0. Price low is a dominant strategy for Company A because no matter what Company B does, Company A's best response is to price low. Great, we can switch it around and think about Company B's best responses to each of Company A's possible actions. Well, if Company A prices high, we're on this row here. Company B could also price high and share the market and get $20, or price low and steal the whole market and get $40. So price low is a best response. If Company A prices low, we're on this row here. Company B could price high and get $0, or price low and get $10. So price low is a best response. Price low is a dominant strategy for Company B because no matter what Company A does, Company B ought to price low. There is one Nash equilibrium in this game which is also a dominant strategy equilibrium, which corresponds to both of our players pricing low. Low isn't just an intersection of two best responses, it's also an intersection of two dominant strategies. This is a prisoner's dilemma, and it's characterized by there being just one Nash equilibrium, which is also a dominant strategy equilibrium, which is also suboptimal. In the Nash equilibrium, both of our companies get $10, but this is not a Pareto efficient outcome. If our companies had colluded and cooperated together, they could have both priced high and shared the market and both got $20 each. $20 each is unambiguously more for each player than $10 each. In the prisoner's dilemma, however, this collusion is made unstable due to these payoffs here, these $40 incentives, which means that for both players, it's the best response for them if their competitor prices high to try to undercut them and price low. The Prisoner's Dilemma is a wonderful game, and I'm going to make a video just on this game, on why I like it so much, as an example of thinking about simultaneous move games. I'll link to that video when I do. Alright, that's it. I hope that this helped. I hope that at least it was a bit of practice and a little bit of exposure to different types of simultaneous move games. Most of all, I hope you guys are having a great day.